Welcome along, ladies and gentlemen, to your weekly SETI Institute talk series. Today we're very fortunate to have as a speaker Rob French, who's a PhD student who's working with Mark Showalter. Sorry, we'll be corrected just in a second. But he's working with Mark Showalter here at the SETI Institute on rings. In particular, he's going to talk to us today about Saturn's F ring. But he's also got a publication coming out on Uranian moons, so look for that. Robert is a self-confessed anomalous SETI person. He comes from a very eclectic background, and he has worked in IT, where he has put together more than 1 million lines of code and co-founded a successful startup company. He has, since tiring of that, he's also been a flying instructor, which he continues to this day, and also a square dance caller, which gives him a great deal of experience in public speaking, which I hope will show through in today's talk. So if you'll join me in welcoming Rob.
Thank you, Adrian. I didn't know that I was a PhD student, but I hope to be at some point. I was a PhD student back in the late 90s, but I quit and went on to other things. So, as Adrian said, I do moonlight as a square dance caller, and so I'm very used to speaking in front of people who all get up and dance. So, if you find yourself just filled with joy learning about planetary ring systems, please don't let me stop you. So, today I'd like to speak about some work that I've been doing here at the SETI Institute with Mark Showalter, and with a bevy of collaborators that I'd also like to acknowledge. And this is on Saturn's F ring, which I think is one of the most interesting objects, personally, in the solar system, Mars notwithstanding. Yeah, I think this needs to be adjusted a little bit. Okay. But before I start talking about the F ring, I wanted to give you a little bit of a background about planetary ring systems in general, just so you'd have some context in which to think about this. All of the outer giant planets in the solar system have ring systems. Jupiter has these gossamer ring systems. They're very, very fine-grained dust, micron and submicron sized. These pictures were taken by New Horizons as it flew past Jupiter a few years ago on its way to Pluto. The top one was taken as it approached Jupiter. The bottom image was taken as it flew away from Jupiter and was looking back toward the sun. And these the rings are very, very dark. They're basically charcoal black, and they are very, very fine-grained dust. The Uranian ring system is also very interesting. It tends to have larger particles. It's also mostly charcoal black, but there are a couple of rings that were discovered at least partially by Mark, that one of which is red and one of which is blue, which are particularly interesting. The top image here was taken by Keck in infrared. Bottom one was taken by the Hubble Space Telescope. Neptune also has a set of rings that are very fine-grained and very dark. They have these really interesting arc structures in them. And finally, of course, Saturn is the most iconic ring system in the solar system, and the one that we'll be talking about today. I'll talk about that a little bit more later, but mainly the thing that's interesting about Saturn is that its ring system is made almost purely of water ice, and they tend to be relatively bright compared to the other ring systems. Also, the ring particles are of a wide variety of different sizes, depending on which part of the rings that we're looking at. As I'm sure you all know, Earth also has a really nice ring system. What you may not realize is that according to this nice documentary that was written in 1958, this is SETI after all, it was placed around Earth as part of an alien invasion. Luckily, as humans managed to beat the aliens away, they managed to move the rings back to Saturn, or else this would be a very, very short talk today. So, why do we study planetary rings? The main reason that people give is that planetary ring systems, the dynamics of the particle motion is very similar to what may happen in early stage protoplanetary disks. And so if we can understand what happens in ring systems, we may be able to understand the evolution of planets a lot better. However, I'm sure that you all know why we really study ring systems, which is that they're really, really cool. Okay, so let's get a little more serious. We'll talk about Saturn here. Saturn has a very complicated ring system. It has the A ring and the B ring and the Cassini division that are between them, which are easily visible from Earth. These are visible in any decent backyard telescope or any really nice pair of binoculars. And I have to say that looking at Saturn through a backyard telescope is actually probably one of the reasons that I got interested in astronomy in the first place. A number of years ago, I was looking in my backyard at Saturn and said, this would be a really cool thing to study. There's the C ring, which tends to be a little bit more transparent, much harder to see from Earth. The D ring, which is almost invisible. On the outside, there's the E ring, which is very, very broad. It consists of all of the detritus that comes out of the Enceladus ice geysers, and the very fine G ring. But what we're going to be talking about today is the F ring, which is this little tiny thing right here. So the F ring, I think, is a very, very interesting structure. It's highly variable. These are a variety of different pictures of the F ring, and you may think that these pictures were taken at widely varying times over a period of months or years or even decades. But the truth is these were all taken in the same 14-hour period. These are just different parts of the ring taken on the same day. And as you can see, there are a wide range of different structures that occur inside the F ring. There are these big clumps. There are these various types of strands and braids. There are these streamers that come out. And these are all highly dynamic, highly evolving structures that change on an hour-to-hour basis inside the F ring. Now, a lot of people enjoy studying the dynamics of the F ring. We're not going to be talking very much about those dynamics today. What we're going to be talking about instead is sort of the macroscopic, the high-level view of what the F ring looks like. So we're going to be averaging all of these structures to get a picture of what the F ring is like as a whole. Okay? But the first thing that you need to realize about the F ring as part of that analysis is that it is extremely variable as you look at it in longitude, and so any one place on the F ring is very different from any other place on the F ring. Before we talk about the second thing that we have to realize with the F ring, I want to give you just a little bit of background on the concept of light scattering. I do not claim in any way that this is a technically accurate picture. It's just a cartoon to give you an idea. But to talk about the two extremes, let's say that I was standing here in front of this spotlight and I was holding a 1 meter sized rock in front of me. There are probably three things that you would realize immediately. One of them is that I'm really not strong enough to hold up a 1 meter sized rock. The second thing is that I wouldn't be able to see anything because the rock would block out the light. And the third one is that the light would reflect back into the audience very nicely. So very large particles tend to do what we call backscatter. They reflect back where the light came from, and they don't forward scatter very much toward someone who's standing on the other side of the rock. However, if, for example, my laptop were to catch on fire and we were to have a little bit of smoke coming up here, smoke has a totally different set of properties. It's very, very fine-grained particles. You probably would see a little bit of reflection of the smoke in the audience, but mainly I would see it coming toward me because the very small particles tend to forward scatter. They don't tend to backscatter. Okay? So depending on the type of particle sizes that you have, the reflection, the scattering of light from a substance looks very different. Thus, if you want to characterize what a ring, for example, is like, you need to look at it at a wide variety of angles and see how the reflection or the scattering of light changes in those different angles. Okay? So with that idea, let's take a look at the F ring. There are two pictures of the F ring here that were image processed in exactly the same way. So these had the same contrast, same brightness applied to them. In the top left, I'm sure you can see this gorgeous picture of the F ring with all of its wonderful detail. Well, I can sort of see it. Anyway, this was taken as a backscatter image. The phase angle here, which is called alpha, of 1. 0 is basically a pure backscatter, so we're looking at it in exactly the same direction that the light is coming at it from. So you can see that in backscatter, the F ring does not reflect very much at all. This is one of the reasons it's almost impossible to see the F ring from Earth, because the sun is always shining toward Saturn in the same direction that we're looking at it. On the other hand, a phase angle of close to 180 degrees means we're trying to look almost directly through the ring at the sun. And in this case, this really bright arc right here is the F ring. So you can see that the F ring changes dramatically in its brightness depending on whether we have backscatter or forward scatter, and depending on what the phase angle is. Now, I think one of the most interesting pictures ever taken of Saturn is this one down here at the bottom. This is Saturn occulting the sun. Okay, this is basically a solar eclipse with Saturn in front of the sun. And the rings look totally different in this forward scatter geometry than they do in the other pictures that you've seen in the past. In particular, look at the really dusty rings here, like the E ring is extremely bright. Here's the G ring. The A ring, Cassini division, and B ring look totally different. But what I want you to notice is that the F ring, which is this little band right here, is actually the brightest of the rings in forward scatter. Okay? This tells us that the F ring is full of very, very small dust particles. Now, everybody in this room is also in this photograph. I don't know if you've seen this before or not, but this is the Earth. You're on the back side of the Earth. Okay, sorry about that. Okay, but I think whoever designed the particular orbit of Cassini to be able to take this picture did a phenomenal job of being able to get Earth in the picture at the same time. This is a little bit photoshopped by NASA. The picture that came out of the spacecraft is not quite so clean, but it's still pretty good. So anyway, we have two things that we need to worry about with the F ring now. One of them is that there's a tremendous amount of longitudinal variation, and the second one is that there's a tremendous phase dependence. Okay? If we want to look at the F ring as a whole, we need to have a bunch of images, some of which look at different longitudes, and some of which have views at different phase angles. So we need to take a lot of pictures. Luckily, Cassini has been around Saturn since 2004 and has provided us with a phenomenally large number of images. We stopped doing this work in 2007. This is somewhat old work at this point. But what we did is we took more than 3,000 images from what's called the narrow angle camera. This is one that has basically a long focal length. It zooms in on the ring very nicely. And what they do with these narrow angle camera images is they basically let Cassini sit in one spot to the extent that an orbiting spacecraft can ever sit in one spot. And they look at one point on the ring, and they let the ring orbit under the spacecraft. And since the ring orbits in 14.7 hours, if you take a 15-hour movie, you basically get to see the entire longitudinal variation of the ring. Okay? Sometimes these have hundreds of images, sometimes they have thousands of images, but we have a very large number of images that have this longitudinal variation. The problem is that there aren't very many of them. There were only 19 of these movies that were taken when we did this work, and so we don't get all of the necessarily all of the phase angles that we would like to see. So we took some of these wide-angle camera images, which have a shorter focal length. You see a much larger amount of the ring, but they were taken at a wide variety of phase angles, and thus we can use those to fill in some of our data gaps. Okay? We took the movies, and we averaged each movie down to a single data point. This is how we got rid of that longitudinal variation and just looked at the ring as a whole. When we did the wide-angle camera images, we took ones that had similar viewing geometries, and we binned them, averaging down to a single data point. But we were still left with 131 data points from the wide-angle camera. And these were all taken with clear filter, no colored images, and from about 3 years, from June of 2004 through March of 2007. Now, one thing we found when we were looking at these images is that something really major happened in December of 2006. This is basically the same part of the ring taken 1 month apart. And you can actually see that some of the structures are sort of similar. You know, this is sort of similar to that, and that's sort of similar to that. But something really interesting happened to the ring during this time period. And it got a lot brighter and a lot wider. And we didn't want this event to mess up our data. So what we did is we took any images that had this huge event in it, and we deleted them from our data set because we wanted to be conservative on these sort of ring changes. Here's an example of how much it affected it. This is a plot of the ring longitude, 0 to 360 degrees, going all the way around Saturn, versus the brightness of the ring as seen by Cassini. And you can see that for the most part, the brightness didn't change from 1 month to the next. But here's that huge explosion of whatever it was that happened in that 1 month period. And so we basically chopped out this data when we were doing our averaging. Remember this, this time period, November of 2006, because we'll be coming back to that much later in the talk. Okay. In terms of what actually caused this, we'll be working on that later. We actually have a number of RAU students, undergraduate researchers, who have been working on this gradually from year to year, and we'll hopefully be working on that again this summer. So how do we analyze one of these images? The first thing we do is we choose an image. This is an example of one of these movies from the narrow angle camera. Each image has 3 types of viewing geometry information associated with it. Alpha is the phase angle. That's the angle that the sun makes with the ring and the spacecraft. So this tells you whether it's forward scatter or back scatter, for example. B is the angle of the spacecraft in relation to the ring plane. So a positive means that the spacecraft was above the ring plane on the northern side. And B prime is the angle of the sun with the ring plane. So this was done when the southern part of Saturn was in its summer. The sun was below the ring plane. So Cassini is above the ring plane. The sun's below the ring plane. We're basically looking through the ring in order to see the sun. So we take one of these images, and we basically draw a box around it. And this box is going to include a little bit of the A ring, just for sort of geometric reference. It's going to go all the way through the F ring and out into the dark side on the other side, and it's going to have a certain thickness to it. And we want to have this thickness because we're able to average the pixels along that width, so that if there's any little tiny variation or something like that, we can average those out. We can also move this box around just a little bit to avoid any sort of bad data, bad pixels, things like that. We then do what's called a light curve, light profile, where we take basically pixel number along one axis, which is starting here and going out, and we measure the intensity of each averaged vertical slice here. And you can see how this corresponds to the end of the A ring. This is the core of the F ring. There's a little blip here that you can't even see up here in the actual image. And this photometric data is in units of what's called I over F. I is the intensity of light that is seen by Cassini, and F is the flux of sunlight that is hitting the ring plane. So I over F is basically the fraction of the incoming sunlight that is being reflected back toward Cassini. Now, this is still in units of pixels. We'll convert this to something a little more useful in a minute. However, first thing we have to do is we have to worry about the background of the image. You see that this is not really, even though it looks black up here, this is not really black down here, and it's not the same black as down here. So what we need to do is find two places that are representative of this background level, and then we need to basically fit a line to them and say that this is the background in that area, and then we subtract it from the photometric intensity. So what we do is we integrate under the curve, and we come up with a single number, which is the area under this curve with the background subtracted. Now, once we've done that, we have something that is basically in units of pixels, but Cassini is of different distances from the ring at different times, and so different pixels have different scales. We want to scale them appropriately based on that distance, and so we compute this thing called equivalent width, which is basically multiplying it by a scale factor so that that particular variable is now removed from our computation. Okay. Now, once we have all that information, what do we do with it? What we can do is we can plot it versus the phase angle. So these filled in circles here, these are those averaged movies that I was talking about. The empty circles are the wide angle camera individual data points, or a very small number of points that have been averaged together. And we can plot the intensity that we measured, that equivalent width, versus the phase angle. And as you can see, the intensity goes up dramatically at higher phase angles. That means it's forward scattering a lot more than it's back scattering, and thus the ring is full of dust. Now, there are lots of things you can do with one of these phase curves. You can analyze it, and you can figure out what the particle size distribution is, for example. But that's not what we're going to be doing. We're going to be comparing this information to Voyager later. But for right now, what I wanted to point out is that this is not a very pretty plot. There's an awful lot of scatter here. And while we know that the F ring has this tremendous amount of longitudinal variation, that's still an awful lot of scatter. Now, we often say in astronomy it's the only science that it's okay to have an order of magnitude error bar, but I still think that we can do a little better than this. Okay? So the first thing that we need to look at is why that scatter might be present. When you have Cassini looking at the ring plane, different pictures are taken at different elevation angles with Cassini above the ring plane. When you look through a ring plane that has a very what's called low optical depth, that means that you can see through it fairly easily, the closer you are to the ring plane, the more deeply you're looking in along the ring, and the more particles you're seeing. That means that something will have a different intensity if you're looking at it at a low angle versus if you're looking at it at a high angle. So what we can do is a geometric correction, where we basically normalize all of our images as if Cassini was looking straight down on the ring plane. And there's a very simple formula to do this. We simply multiply it by the sine of this angle, and this should fix everything. So let's look at what happens. Here was our original plot with a lot of scatter. Here's what happens when we do that initial geometric change. So here's the original, here's the new one. Okay, this does look a little better, but there's still these annoying data points that are hanging out here at the bottom, and that look like they have too much scatter. That means possibly that this geometric correction that we did is not really the correct correction to do. One of the ways that we can tell this is that we can color code them based on the angle of Cassini above the ring plane. And what you'll notice is that these outlier data points are the ones that were measured when Cassini was extremely close. That's B in degrees, so 5 degrees. Cassini was almost lined up with the ring plane, looking very deeply into the rings. Those are the outlying data points. On the other hand, the ones where Cassini was much higher on the ring plane, looking more through the rings, are the ones that line up very nicely. This tells us that our assumption about the ring being a very low optical depth may not be correct, and we can't use that geometric correction formula that we just had. So how do we fix that? Well, we have to assume that shadowing, that is, that ring particles are in front of other ring particles, and the sun, as it illuminates ring particles, there's more and more shadow as you go deeper into the ring. And we also have to assume that obscuration is important, that is, that as you're looking into the ring plane with your camera, you can't see more and more particles the deeper you look into the ring. There's a very common set of formulas to handle this. This will be on the test. But all of the variables in these formulas are things that we already know with one exception. So B is the angle of the spacecraft above the ring plane. B prime is the angle of the sun with the ring plane. Mu and mu naught are simply the signs of those two angles. That's easy to handle. But there's one thing that we don't know what it is, and that's tau. Tau is the optical depth of the ring. There are lots of different ways you can measure optical depth. The most common way to do it is by doing what are called star occultations, where you have a star pass behind the ring. You look through the ring at the star, and you see how much of the starlight has been eliminated by passing through the ring. The problem is that, as we've talked about, the ring is tremendously variable, and if I have one star occultation in one part of the ring, there's no reason to believe that that particular optical depth is relevant to any other part of the ring. So what we have to do is we have to go back to our original idea here and say, what are we trying to accomplish? And what we're trying to accomplish is basically make that graph look pretty by getting rid of the scatter. Okay? So what we can do is we can explore different values of tau and look at how much scatter there is on the plot for a particular value of tau. And we can find the tau that minimizes the scatter on the plot. I'm not going to claim that this tau has any particular physical interpretation. It's sort of an average tau for the ring that happens to minimize the scatter. But if you measured the optical depth at any one point on the ring plane, there's no reason to believe that you would actually see this particular optical depth. So what happens when we apply these formulas? Well, here's what we have with the scatter, and here's what happens when we do that adjustment. Okay, so now I think it's getting pretty. This is something that I'm willing to draw a curve through now. And in fact, we'll do that in just a moment. So now that we know how to do the data processing, we can do exactly the same thing with Voyager images. Now, the Voyager images were not nearly as pretty as the Cassini images. I admit that I'm very spoiled looking at Cassini. Mark is always telling me this, that he had to walk uphill both directions in the snow in order to analyze his Voyager images. Thankfully, he gave me his data so that I didn't have to do any of that hard, cold work. So we took the images that he had done for a previous photometric study of the F-ring, which was published in 1992, and there were many fewer images available at that point. Voyager didn't hang around Saturn for all the time that Cassini has been there. It was there for basically a day. And these were taken during 2 passes. 1980 was Voyager 1, 1981 was Voyager 2. And here's the set of data that we have from Voyager 1 and Voyager 2. The solid filled-in triangles are from Voyager 1. The empty triangles are from Voyager 2. Once again, we've color-coded them based on the angle that Voyager made with the ring plane. Now, this is not nearly as pretty as our Cassini ones. We can do the same trick we did with trying to figure out what that optimal tau was, and we get that. We do have this one little data point, this poor blue data point, which is the one that when we were close to the ring plane, that's the outlier, and it does kind of fall in line. But this is certainly not as well a behaved data set as we got with Cassini. Once we have these 2 data sets, though, we can now overlay them on top of each other, and we can fit curves to them. So this bottom curve is fit to the Voyager data. This top curve is fit to the Cassini data. And you can tell, first of all, that they more or less have the same shape. It turns out that if you actually analyze the shapes, they're almost identical, which means that the particle size distribution didn't change between Voyager and Cassini. But what's really interesting is that no matter where you look, the Cassini images are brighter than the Voyager images. And this difference of more than a factor of 2 was very unexpected. We were not planning to see this when we started this project. So let's just review here very briefly. Actually, sorry, let me go one more thing first. Do we believe this answer? When we first saw this, that it was twice as bright as it used to be, we didn't really believe that this was true and thought maybe there was something wrong with our data processing. So there are a few things that we looked at to try to prove that this was not true. One of them is that we looked at the absolute calibration. So Cassini has a nice CCD camera. It's relatively modern. Voyager has this ancient Vidicon thing that most people don't even know what they are these days. And they went through different processing pipelines, different calibration pipelines. How do we know that we were actually, when we got the I over F values out, how do we know that they were actually calibrated properly? So what we did is we looked at the A-ring. We figured that the A-ring was not expected to have changed over that 25-year period. It doesn't have any significant amount of variation, either in radius or in longitude. You can average a huge part of the A-ring and get one value out of it. And we can get images that have more or less the same viewing geometry between Voyager and Cassini so that we don't have to worry about messing up our geometric corrections. So we found a few of these images. We found 9 of them. We looked at their intensities. We took their ratio, and it was basically 1. Any small error bars that we have there are certainly dwarfed by the factor of 2 change that we think happened in the ring. So we believe that our absolute calibration is correct. Another thing that we can look at is the color of the ring. So again, Voyager and Cassini had very different cameras on them, and the cameras had very different sensitivities to different wavelengths. So the Voyager Vidicon camera is very sensitive in the blue and is almost completely insensitive in the red, whereas the CCD cameras tend to be very sensitive to the red and less sensitive in the blue. This means that if the ring had a very red color, we would expect it to look much brighter to Cassini and much dimmer to Voyager. So how do you look at this? Well, we managed to find a number of images. We found 51 sets of images where Cassini had taken pictures through colored filters of the F-ring, and they were just bang, 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 one right after another, where they just flipped from one filter to the next. So it was the same place on the F-ring. There was no chance for the F-ring to have evolved during that very short period of time. And if you overlay them on top of each other, I just did this in Photoshop. This is sort of a hack job, but you get this nice, gray-white ring just to show you what it looks like. If you do what's called, you analyze the spectral slope, where you basically look at how the intensity changes from the red to blue across all of these images and average them all together, you get 1. This means that the F-ring is basically gray, and there's no excuse for Cassini to have seen more red than Voyager saw blue. The final thing that we can look at is how it evolved over our 3-year observation period with Cassini. If we think it's changed over 25 years, maybe it also changed over 3 years. So our data set broke down very nicely into 3 different time sets here, and we fit individual curves. I constrained the curves to be the same shape, but they all were fit to different sets of data points, which are colored here based on the time ranges. And what you can see is that basically they didn't change at all during those 3 years. And in fact, there's no systematic movement whatsoever. The blue here is the earliest. It's on top. But the magenta is the middle one, and it's on the bottom. The yellow is the latest one. It's in the middle. So there was no consistent change in the brightness of the ring over time. So at this point, we really do believe that the F-ring is twice as bright as it used to be. We think it's of a moderate optical depth, not a low optical depth, and we had to do that much fancier version of geometric correction. And we know that this particular difference isn't due to any sort of absolute calibration problem, color of the ring, or short-term variation. So it really is twice as bright. So in order to figure out why it's twice as bright, we need to talk a little bit more about the ring itself. We know that the F-ring has a bunch of reservoirs of little aggregates of particles in them. If you do these these occultations of stars, you can see little clumps inside the F-ring. Now the F-ring exists very close to Saturn's Roche limit. Anything inside the Roche limit will tend to be torn apart by the tidal forces of Saturn. And anything outside of the Roche limit will tend to aggregate and clump together into little moons. The F-ring, being right at Saturn's Roche limit, basically can't decide whether it wants to be a ring or whether it wants to be a moon. So anything that comes in and perturbs it a little bit is likely to break apart any aggregates and produce more dust. This doesn't mean there's more material in the ring. It just means that it's been spread out more so that it will reflect more light. Okay? We know that these things are constantly breaking apart and reforming because you can see them. If you remember that image back in the beginning with all the different variation, those clumps that I showed you, they break apart and they reform all the time. Now, whenever we talk about dynamics of the F-ring, there's always one giant space potato that comes in as the cause for all of this, and that's Prometheus. This is a great picture that was just taken very recently. Prometheus is a very small moon, but it's one of the 2 moons that borders the F-ring. Prometheus is on the inside between the F-ring and the A-ring, and Pandora is on the outside of the F-ring, and basically they're not quite shepherd moons, but they do help confine the F-ring to its location. Now, Prometheus and the F-ring have a very interesting relationship because they have orbits that are both slightly eccentric, and because they're eccentric and we're orbiting around an oblate planet, Saturn is very oblate because it's gaseous and it spins fast, they precess, but they precess at different rates. So what this means is that, let me show you what this picture is here. This is going to be a movie in just a moment. But when you have an ellipse, this is Saturn here in the middle, even though it sort of looks like the sun. And this is the orbit of Prometheus, and the white one is the orbit of the F-ring. Whenever you have an eccentric orbit, there is a part of the orbit that is closest to the central body. And that's called the pericenter, and that is marked with this red arrow here. Likewise, for the F-ring, there's a part of the orbit that's closest to the central body, and it's marked with the white arrow. Now, as they precess, those pericenters are not always going to be lined up, and they're not always going to be opposite each other. They're going to change over time. Whenever the pericenters are aligned, as they almost are here, you can see that there really aren't any places between the two orbits where they are very close to each other. On the other hand, as you'll see in a minute, when they're opposite each other, the orbits can get very close to each other, and that allows Prometheus to make various types of it interferes with the F-ring. Now, we had a small technology glitch this morning with this movie. Ignore the man behind the curtain as I do something secret here. And poof, we're on a different computer where this movie actually plays. Okay, so here they are. They're aligned, and you notice there isn't very much chance for them to interact. But as they precess at different rates and they become anti-aligned, notice how the orbits have one place that gets very, very close together. Now, this is just a generic cartoon of precessing orbits. This is not meant to be representative of Prometheus and the F-ring, because I wanted to show this to you in a way that was easy to see and that was fast. But in a second here, I will show you what really happens to Prometheus and the F-ring. So once again, we have white is the F-ring, we have red is the orbit of Prometheus, we have the arrows pointing the pericenter. But there are a couple things that are different about this. One of them is that the precession rates of the F-ring and Prometheus's orbits are accurate in this movie. Okay? However, I did magnify the eccentricities of the orbit a lot so that you could see when they're far apart and when they're close together. The other thing that I did different here is, because it's very hard to see as they're all rotating around each other, is we're going to be watching this movie in a frame of reference where the F-ring is stationary. So our camera looking at the F-ring is going to be following the F-ring around. The F-ring will appear not to move. And what we're going to see is the relative change of the orbit of Prometheus with the orbit of the F-ring. Now, at each point where the two ellipses are closest to each other, I have this little blue line drawn. And what we're going to plot down here at the bottom, and these are real dates, is the distance between Prometheus and the core of the F-ring. So the yellow lines are indicating when Voyager 1 and Voyager 2 were present. In a moment, we'll see when Cassini was present. But you can see there's this really interesting interaction here between the rings when they're viewed from the point of view of a rotating F-ring. And there's a huge difference in the distance between Prometheus and the F-ring. It goes from below 200 kilometers away to about 700 kilometers away. So you could imagine that if Prometheus is really 700 kilometers away, it wouldn't be making very much difference to these aggregating particles in the F-ring, but when it gets very close, maybe it would be. So there are a few things that I want you to notice about this plot. One of them is that during the Voyager flybys, Prometheus was a lot further away than it was during Cassini. This is one reason we might believe that the ring got brighter during the Cassini tour. The second thing that I want you to notice is that around 2015 or 2016, the distance between Prometheus and the F-ring is going to return to about the same separation that was present during the Voyager flybys. And we'll talk about that in the future work at the very end here. And the last thing that I want you to notice is this little star right here. You remember at the beginning I asked you to remember the date November of 2006. Well, this is November of 2006 when this happened. And it just so happened that a few days before this happened, a movie was taken of the interaction of Prometheus and the F-ring. Now, I'm not going to claim that this particular interaction of Prometheus and the F-ring caused this. Correlation is not causation, but it is sort of an interesting set of events that happen at the same time. So this is a famous movie of Prometheus. It's going to come up into the F ring, basically. It's going to go into shadow for a moment, so it's going to go black. And then it comes back out again. And you can see how much it disturbs the core of the F ring, and it draws one of those streamers out. So it's very reasonable for us to believe that Prometheus is the cause of the increase in dust of the F ring. This is a great movie. All right, now I'm going to return to our secret local presentation. Okay, there is, however, one very large problem with this theory. As we always say, theories are great until they meet their first ugly fact. And that is that we looked earlier at how much the F ring's brightness varied over that 3-year period that we were looking at it. And if you look at the distance between Prometheus and the F ring, you notice that it changed tremendously from 2004 to 2007. Thus, we would expect that the ring would have gotten a lot brighter in 2007 than it was in 2004, and it didn't. So honestly, at this point, we don't know why the ring got brighter. It could have been random. We know these things happen. It still might have something to do with Prometheus, but we have a result that we don't really have a very good explanation for. So talking about future work here, we know the Cassini mission has been extended, which is pretty amazing. It showed up at Saturn in 2004, and it's going to stay there until 2017. This is the extended mission. They already had the extended mission. And as we showed you a moment ago here, the Prometheus and F ring distance is going to return to those original Voyager levels in 2015 and 2016. Assuming Cassini continues to work, assuming I'm continuing to work here, and assuming Mark continues to fund me for this work, hopefully we will be able to look at the F ring during this time period and see whether it returned to the Voyager levels of brightness. If it did, then maybe there really was an interaction between Prometheus and the F ring, and if it doesn't, then we're going to have to come up with some sort of other explanation. Okay? Also, we know that all of those clumps are forming and breaking apart all the time, and there's a lot more work that we can do in order to look at the relationship of the formation of those clumps to the position of Prometheus, and that's some of the things that hopefully our undergraduate students will be working on this summer. So I talked very fast. I'm concluding a little bit early here, but basically we know that the ring is twice as bright as it was 25 years ago. We know that it's probably due to an increase in the amount of dust that's present. It's not that there's more material in the ring, but that the dust has been spread out more so that it reflects more. We don't know what caused this, and we're hoping that longer-term observations are going to help reveal this mystery.
Rob, could I start off with a question?
Of course.
Well, you got a optical depth of 0.089 for the Cassini observations.
We got a tau of 0.089,
Sorry.
which I'm not claiming is an actual optical depth.
All right.
Yes.
All right. So with those caveats, what did you get for the Voyager minimization?
Oh, yes, yes. If you go back and look at it was really not very exciting, but if you look on the left here, you'll see that it says that Voyager was 0.024, and Cassini was 0.089. So it's really hard to say that this is actually meaningful because the Voyager data had a really hard time. We had a really hard time reducing the scatter of the Voyager data. This just happened to be the number that reduced the scatter, but it didn't really reduce it a lot, right, as I showed you. So it's hard to say whether this has a physical meaning or not. But it is true that maybe it's suggestive that the tau for Voyager was significantly less than the tau for Cassini.
Right, which would also explain the variations in brightness.
It would, and you may be interested to see.
Well, it wouldn't explain them; it would be correlated.
It would be correlative, exactly. So these are some examples of actual optical depths that were measured by the VIMS instrument on Cassini. And as you can see, this is the core of the F ring here. And as you can see, there's a tremendous amount of difference in the optical depth in different places. Sometimes it goes up to 0.8. Sometimes it barely gets above 0.1. And this is what our 0.089 looks like, which is sort of a nice integrated average. But again, it's very hard for me to claim that that has any sort of physical implications to it, other than it reduces the scatter.
Right, and the actual streaming that we were seeing occurring, what's actually happening there? I mean, can you take a best guess at what's actually
I think I
happening?
would leave that for someone who's actually a dynamicist.
All right. Anyone in the audience?
Well, I'm not a dynamicist, if you want someone to answer that question. I don't really. Okay. So I'm punting on the dynamics question. Maybe we can hand this back over to Mark later. I had a color question. So you looked at the color of the ring during Cassini and found that it was basically white, or basically, grayscale, right?
Correct.
Did you look at the color during Voyager?
People have looked at the color during Voyager. Of course, the problem with Voyager is that it had a much narrower frequency response.
Right, but you can at least go from, UV out to orange if there are color images taken.
Right, and by the way, we actually did go into the infrared and into the ultraviolet. I didn't mention it there, but we did go out just to see if there was any difference.
Right.
And we didn't see any difference
Okay,
there
so
or
it's
not.
it's not that it had a color during Voyager and then lost it by Cassini.
I don't
right?
believe so.
Okay.
Mark, do you know anything different?
The color from Voyager, I don't know if it's ever been published by anybody, but other measurements, including some from Hubble, just say it's pretty much equal.
Okay.
Which, of course, is different from the rest of the rings, which have a very slight reddish tinge to them.
Did I see a question over here?
Rob, I was really struck in the movie with the streamer that came off when the interaction occurred.
Everybody
and
loves the streamers.
And also the fact that there were many streamers in some of the early pictures you showed of the F ring.
Yes.
So I wonder, do you see in the data a correlation between the number of streamers and the close proximity or distance of Prometheus and Pandora from?
Oh, sure, absolutely. That's a given. So what happens here is that the orbital period of the F ring and the orbital period of Prometheus are, of course, slightly different because Prometheus is closer to Saturn. And so every time Prometheus comes around, its point of closest approach to the ring is 3.2 degrees further along in its orbit. So basically every 3.2 degrees, there's another one of these streamers. And you can see there's basically Keplerian shear that's happening here that's inside the ring that is taking one streamer and is then changing its angle once it's 14 hours old or 28 hours old or whatever. And so, yes, these obviously appear much more when Prometheus is close to the ring, and they don't appear so much when Prometheus is far from the ring. That's not really something that we've been looking at, but I think it's pretty much a given.
With regard to the streamers,
I'm not a streamer guy.
speculation. Are we dealing with static charge on the vehicle itself?
This is gravitational, right? But yeah.
I can address that because
Here, you want to? Why don't you give Mark the mic so it's on the tape?
This is a topic that quite a few people have studied going back to the Voyager days, and there are a number of people on the imaging team currently who are studying it. But essentially, it's a gravitational interaction. What happens is Prometheus is about 100 kilometers. It's not a small object, really. And when it goes into the F ring or goes near the F ring particles, it adds a little bit of gravity, its gravity, to the net gravity that they're experiencing from Saturn. Some particles speed up and others slow down because of the nature of the direction that the gravity is pulling on them, and that forms these streamers. So it's purely gravitational. It shows up in simulations almost exactly the way you can see it in the movies.
So it's a clumping effect of the particles that
There, it has nothing to do with the particles themselves, in the sense that it is not a clump. The particles aren't touching each other. There is no collision involved. It is simply that Prometheus's gravity rearranges the particles as it passes through the ring. It changes the orbit of each particle a little bit in such a way that some speed up and others slow down, and you get these transient features that we see.
There's the famous simulation movie of.
Oh, great.
Right.
And Rob, it looked like the closest approach was like happening 2010 or
Yeah, December of
2009.
2009 was closest approach.
And did you get a set of
So we have not looked at
data?
those images yet.
But you have
that's
them
how
waiting in the wings.
Yeah, well, they'll be coming into the PDS, and then obviously that's something we need to look at.
Is there anybody who's doing like an n-body simulation of the F ring, considering
But that's what this is.
considering the two moons as well? This is only
Well,
with Prometheus.
Well, this is only,
right?
yeah, Pandora doesn't really have that much effect on the ring.
Okay.
This is Carl Murray's work. Yeah, he's probably one of the primary dynamicists working on the F-ring behavior.
Yeah, but this is a short scale one. This is not a simulation during over 20 years where you see a change of the distance
Oh,
between
that's
the
true.
moon.
Yes, I don't know of anyone who's doing that sort of a long-term.
Because that's what you see, basically, most likely.
Any thoughts on the origin of the ring and why it's so different from the other rings in terms of its albedo and stuff like that?
Well, the albedo of the F ring is not that different from the albedo of the rest of Saturn's rings, but Saturn rings obviously are different from the other planetary rings.
Well, it's grayness, sorry.
It's well, there are conflicting ideas about why the main rings are a little red. Certainly, the one of the more spoken about reasons, which has been touted for 30 years, is that there's a little bit of iron that has an intimate mixture with the ring particles. And it can't be big chunks of iron, it has to be actually intimately intermixed with the molecules of water. But from a spectral point of view, that seems to be one way that you can account for the red color. You also have to put a little bit of carbon black in there as well. Right. But there are no obvious spectral features. You can see the water spectral features, but you can't see any sort of organic spectral features when you look at it in the infrared.
Okay. And
and in terms of the origin?
Yeah, I'm going to pin you down on that one.
Well,
you've been very political in your
well, there are certainly lots of theories about the origin. People have talked about comets. People have talked about moons. The one that hit all the news recently from Robert Canup was that a differentiated moon early in Saturn's history had ice on the outside and had a rocky interior, got a little bit too close to Saturn. The icy exterior got tidally stripped away, formed the rings, and then the moon went elsewhere and left behind the rings. And she did all of these very complicated numerical simulations to show that that might be possible.
And that it differentiates the rings as we see them, and
no, I don't think there's any. I don't think that they went quite that far. Now there are lots of resonances in the rings, like different satellites of Saturn cause different boundaries in the ring. So, like the edge of the A ring, for example, is a very clean resonance. The inky gap in the ring has a little tiny moon pan that helps clear it out. Various other structures are caused by various other resonances. So you would have to take into account all of the satellites and all of their resonances, as well as a large number of very small bodies that exist in or near the rings that we don't even have resolved images of or necessarily even know are present, to account for the detailed structure of the rings. I think we are far from having a complete understanding of those things at this point. And certainly there is no consistent or uniformly accepted explanation as to where the rings came from at this point, or even how old they are.
Okay. We have one more question.
What are the range of particle sizes that we're dealing with?
So they're different depending on which particular rings we're talking about. If we're talking about the F ring, these are submicron, micron sized for the most part, up to, that's the dust that we're seeing for the forward scatter, up to aggregates, which are small numbers of kilometers. In the other rings, like in the B ring, for example, the particles tend to be centimeter to meter sized, much less dust and much more big particles. So every ring is different in terms of its particle size distribution.
Okay, Rob, well, we have a special memento here, which I've taken
my own
out of
mug?
its box. Yes, it's your own antique SETI mug in commemoration of a great talk. So
Thank
you'll
you.
all join me in thanking Rob.